Plasma and fusion demonstrations. Part of a series of activities in plasma fusion physics to accompany the contemporary physics education project chart, Fusion, Physics of a Fundamental Energy Source. Properties of a plasma, half-coated fluorescent bulbs. In this segment, we will set up and view a half-coated fluorescent bulb and study some of the properties of the plasma that is inside of an operating fluorescent bulb. Equipment setup. The equipment used for the following demonstrations includes a half-coated fluorescent bulb, a high-voltage power supply, connecting wires, a Tesla coil, a diffraction grating, and a large magnet. One end of the black lead is connected to the power supply ground and to the negative 125 volt connection. The other end of this lead is connected to the clear side of the fluorescent bulb. One end of the red lead is connected to the positive 250 volt connection. The other end of the red lead is connected to the other side of the fluorescent bulb. The power supply is then turned on. Set on low current, a Tesla coil is held briefly to the positive end of the bulb to induce a spark and light the bulb. The difference between the violet light from the uncoated or clear side on the left and the white light from the coated side on the right is evident. Notice that due to the phosphor coating and the properties of fluorescence, the white light from the fluorescent coating is brighter than the violet light from the glowing plasma seen inside the tube on the clear side. Investigating spectra. Using a diffraction grating to view the bulb, a distinct difference is definitely noted between the two sides. Please note that the bulb can be seen at the bottom of the screen and the spectrum is seen above the bulb. The yellow light under the coated portion of the bulb is glare and is not part of the spectrum. When viewing just the coated end, a continuous spectrum is observed. When viewing the uncoated end, only the bright lines characteristic of a gas are visible. Compare the two sides, uncoated on the left and coated on the right. Comparing the fluorescent tube spectrum to the spectrum of a mercury tube. We will use both a half-coated tube and a mercury tube in this segment. Here we are viewing the spectrum of a mercury vapor tube. Notice again the bright spectral lines. Now, on the far left is the mercury vapor tube. In the center is the uncoated fluorescent bulb, and on the right is the coated bulb. Notice how the spectra of the mercury vapor tube and the uncoated bulb match. Also, notice that the mercury spectra is superimposed on the continuous spectra of the coated side. Comparing the fluorescent tube spectrum to the spectrum of an incandescent bulb. In this segment, we will use the half-coated tube, a variac, and a tungsten incandescent bulb. When comparing the coated fluorescent tube spectrum on the left with the incandescent bulb spectrum on the right, note the stronger violet section of the fluorescent bulb and the stronger red section of the incandescent bulb. Observe that for the incandescent bulb, there are no superimposed spectral lines as are visible in the continuous spectrum of the fluorescent tube. By decreasing and then increasing the incandescent bulb intensity, one can observe the fading of the violet sections of the spectrum. Keep in mind that as we are changing the incandescent bulb's intensity, we are changing its temperature. The effects of a magnetic field. When observing a lit bulb, a gap between the filament, the red dot, and the beginning of the violet glow of the plasma should be visible. In this dark region, the electrons are gaining enough kinetic energy to excite the mercury atoms out of their ground states. Because the plasma within the bulb is composed of moving charged particles, bringing a magnetic field near the tube causes a deflection of the particles and therefore a visible deflection of the glowing plasma within the fluorescent tube.